All right, so once we have determined if your reagent go either strong or weak, right? Strong go as E2 or SN2, weak go E1 or SN1. All right, we're going to use the structure of an alkyl halide as a tiebreaker to help you determine which way it will go, and you can like pin it down which mechanism exactly, right? Most of the time, you're going to get the mixture, maybe like a couple mechanism, but at least one of them going to be major. All right. So, all right, we're gonna look into the structure of alkyl halide this way. Let's take a look. Steric effect, and do they allow elimination or not? The anti-periplanar beta hydrogen. That's the key. Okay. All right. Start with the steric effect. So just to remind you, if this guy is a strong reagent, sulfide is a strong reagent. Of course, I'm gonna do SN2. Right. So, but it cannot do it if bromine doesn't leave. So I tell bromine to go away, come out. Bromine say, nah, I'm not leaving because sterically hindered of the structure of this alkyl halide, which means that this reaction is gonna be no for SN2. All right, this is a steric effect that we're looking for. Now, anti-periplanar beta hydrogen, it allows you to do an E2. Look something like that. That's an E2. Right? If your alkyl halide doesn't have a beta hydrogen, you cannot do an E2 there. There's no E2 product there. All right? You're going to be no reaction. Okay? That's what we're looking for. We look at the steric effect first. And for the elimination, you're going to look at if it allows E2 to happen or not. All right? So, look at it right here. All right. I'm going to just start with this guy right here. All this acts only as a base, as a weak nucleophile. So, they don't do SN2. This is a strong base, only E2. All right? So, as long as any of these has one beta hydrogen. As long as it got one beta hydrogen, they can do all E2, 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 doesn't matter. This is all going to do E2 anyway. As long as this guy have beta hydrogen, E2, go. All right. If you see this reagent in the reaction, totally E2. All you have to do is just look for beta hydrogen. If it doesn't have beta hydrogen, then it cannot do E2. If it does, totally go E2. Right? And you don't even have to worry about substitution. This guy never do substitution. Okay. All right. This one is an easy case. All right. So this group number 3, do only nucleophile, do only SN2. Right? This guy do only SN2. Weak base, so it won't go elimination for sure. Strong, totally go E2, not E1. All right. All right. When you add this with the primary alkyl halide, this is the best substrate for an SN2 reaction. Totally go SN2. All right. Secondary alkyl halide also it's good. A little bit higher steric hindrance, but SN2 can operate. All right. Now the problem is down here. Listen to the logic. Make sure you understand the logic behind it. What do you know about tertiary alkyl halide with an SN2? What did you know about it? It blocks backside attack. Remember that? It blocks backside attack. When you add this guy, let's say iodide. Add iodide here. Iodide want to attack from that angle, from backside from the leaving group, right? But all these methyl groups are too strictly hindered. Iodide cannot access that carbon. What can iodide do? Can it act as a base? No, this is a weak base. Iodide is one of the weakest base. It won't grab hydrogen, right? What happened? So only one option for iodide. Iodide gonna wait until solvate this compound and become carbocation. And you know, when a compound becomes carbocation, it got space front and the back. Iodide can attack right there, or sulfide can attack, whatever nucleophile can attack there. And this also a substitution reaction, but it's not SN2 anymore. What mechanism is this? This is an SN1. This is an SN1 reaction. Yeah, watch out for racemic mixture. All right. So strong nucleophile can go SN1 only with tertiary, but please don't memorize like that. That's the last thing I want you to do. Memorize, oh, strong nucleophile, go SN1 only with a tertiary. No, look at the logic here. Wide open, a small substrate, love SN2. This guy can go SN2 anyway. After that, go SN2. A little bit higher steric hindrance, still go SN2. Too high steric hindrance, block backside attack right away, no SN2. So the only thing that this guy can do is wait until the alkyl halide become a carbocation, and then the nucleophile can go attack. But right here we call SN1, not the SN2 anymore. All right, that's for the strong nucleophile. Okay, so SN2, SN2, and then SN1 only for tertiary alkyl halide because steric hindrance. All right, with the same logic here, we're going to use it with this group number 2. All right, this group is problematic because it can do both a base and a nucleophile. They're strong. They're going to go either SN2 or E2. So SN2 and E2 are in competition for these guys. All right, they are in competition. But here's the thing: if they react with the primary alkyl halide, SN2 dominate right away. SN2 dominates. Usually substitution it happens easier and faster than E2. E2 takes a lot of energy to do elimination. Okay, so usually SN2 dominates. But now, if we switch the structure of the alkyl halide to tertiary, to secondary alkyl halide have more steric hindrance, slow down the rate of SN2. Right, slow down the rate of SN2. When SN2 is slowed down, E2 still go as normal. So E2 become dominant in this case. Say one more time. I go back right here real quick. So this guy are strong base, are strong nucleophiles. They are strong bases, are strong nucleophile. They can go either SN2 or E2. All right. So mix this guy react with the primary alkyl halide. SN2 dominates. Now usually SN2 takes less energy than the E2, so it go faster. So E2 become major product. But once you switch the structure of substrate, that use the one that have more steric hindrance, this steric hindrance slow down the SN2, slow down SN2 enough that E2 dominate. E2 beat SN2. In this case, you're going to have E2 as a major product. All right. Now, what happened if I use tertiary? What happened if I use tertiary? Oh, totally block SN2. In this case, this guy gonna go just E2, only E2 product. Did that? That's the logic behind it. You use a steric hindrance to help you determine the product. All right. So less steric hindrance, go SN2. Higher steric hindrance, slow down SN2 enough for E2 to compete. And this guy block SN2 totally, absolutely block SN2. So only E2 can happen. All right. So that's what happened when you determine the possible mechanism of these guys. Okay. And lastly, the easiest one: weak base, weak nucleophile. With so the only reaction that this guy will do is either E1 or SN1. Does it make sense? This guy a weak reagent can go either SN1 or E1, which must pass through stable carbocation. Okay, weak base, weak nucleophiles gonna go either SN1 or E1, which pass through stable carbocation. Primary alkyl halide not stable enough to do it. No reaction. Secondary, stable enough to do SN1 and E2, but practically it gives you such a low yield. Practically no, it doesn't do it. Tertiary, that's a good substrate for carbocation, right? So it's stable enough to do carbocation. So SN1 usually don't dominate, except when you heat it up. When you at under elevated temperature, E1 become dominant. But we usually heat it up, basically, because these guys are so weak. They don't really do anything. We have to heat it up to speed up the reaction. Otherwise, it's gonna be way too slow, right? So, and every time when you heat it up, elimination dominates. Okay. All right, let's do this together on the next video.